Hi, my name is Bernard Brault, and I'm doing a third video on the coronavirus infection and the models that I use to predict the infection rate in the population. So I've done two other videos before, as I said, and I'm inviting you to look at them. Just to recap, I'm using an SEIR model, so it's based on different buckets, and it starts with the susceptible bucket, which is the population. We're all sitting in here. Gradually, people are moving from this, getting somehow infected, but there's an incubation period where at first, they're not propagating the virus, and after a while, they become fully infected, and they move to this third bucket. Once you're fully infected, then you somehow either recover or die, and that's the last one. And as the equation that describes the flow between these different compartments, if you want, are differential equations over time, and they're described here. So people are flowing out of being susceptible into being incubated, and the minus ASI shows up positively. That's the arrow in there, and then people are flowing out there. That's the negative with here with the A and B parameters, and you're just going from across this. Now, if you build a model like this and you run it, you realize that there is an important parameter, actually a ratio, which is A over C right there, and we call this the R0 ratio. And it's basically how many people are getting infected by somebody else. It's how virulent, so R0, if it's one person infects another, and so on. But if R0 is 4 and 1 infects 4, it grows to 4, and 4 to 4 is 16, and this is where you get the exponential growth. And R0 can be changed over time. It varies over time, and that depends on our behavior, and this is why we're talking about flattening the curve, isolation, social distancing. What we're trying to do basically is drive R0 down to something below 1, so that the infection can taper off. Moving to the next slide, all right, so in this case here, I'm mostly interested in the number of people are infected and looking at how R0 is evolving over time, more specifically in the province of Quebec, where I've got some data. If I look at the SEIR model, I'm not so much interested in how people go from being infected to recovered. Either they do this on their own, they go to the hospital. I'll let the doctors figure this part out. I'm sure it's the most important part for them, but not for the modeling here. So what I want to show you now, if I look at the whole model here as one big box, right, the input of this box would be R0. And if you modify R0 by driving down A, then the infection rate, the propagation of the virus slows down, and it's measured in the output by the number of infected people right there. So the next step is how do I estimate this R0? I'm sure if I did, a good study of these equations, then they don't look so complicated, but they're not linear, so it is a little more tricky. But I'm sure there's ways to figure out what these values are, but I came up with my own trick to estimate this, and I'll share that with you. This is the actual population. So this is what's really happening out there, and when we're getting data, we're saying so many people are getting infected. This is the measure. These are the data points, and every day there is a new data point. So many new people got infected. Here's a number of infected people, and so on. So the measured data right there, right, is the something that we actually measure. We get in the news every day. But what we don't know is what is the R0. We know it's going down, right? We can see it from the graphs, and we see it smoothing out, and we're isolating and so on. So how can I figure out the R0? And that's what I'm trying to do here over time, right? So I built this model, and you can see in the past what I've done with the model, and its output somehow matches more or less the input there, and I'm matching this by manually adjusting the R0. So what I want to do now is show you that I think I'm going to automate this, and the way I automate this is I'm going to look at the difference between the actual data and my model output. That's going to generate an error signal in my infection rate. And based on this error signal, I'm going to feed this into a filter, and the filter will make an adjustment in the R0. And the idea is, if I can drive the error down to 0, that means that the measured data and the model output are equal. If the output of the two are equal and the model represents what's going on, then I should have a good estimate of R0. And that's what I'm going to look at ultimately as my output. Alright, so let's take a look at this. And using Excel, and you've seen this before, this is the time axis if you want. This is time 0, day 0, day 1, and so on. This is the number susceptible going into incubation. Finally, this is the bucket I here of number of infected in percentage. And for a population of about 10 million, this is the number of rates that are infected. And the data from the Quebec population, I'm starting to get decent data starting at around 1,000 cases. So let's scroll down to where we are more or less today. I think today we're more closer to 10,000. But here's the first Quebec data point that I have. And as you can see, it's very close to the model output at this stage. And looking at a 4.15 R0, that's where I started. And the chart that you see right there, the first chart, and let me just maybe zoom in a little bit and show that to you. So the first chart right there in blue, the blue dots are the actual measured data, and the last one I got from yesterday is right there. And that point, if I scroll down, I'll show you where it is. I think that's the latest data point, 10,900 cases, and yesterday was 10,031. So those are the blue data points. I didn't want to use the blue points because they're a little, you know, they're noisy and so on. So the first thing I did is I interpolated and then I smoothed out the points a little bit. Didn't want to smooth it out too much because I don't want to lose the resolution or the granularity in the data. But that's what I started doing, and this is in yellow there. The line that you see there is my smoothed data, and that's what I'm going to use here in order to calculate my error signal. So this is the number of actual case. This is the cases with interpolation in between, and interpolated smoothed out data. And I'm using like some kind of a low-pass filter to do this. Finally, before I calculate the error, here's the smoothed out percentage of people that are infected. And if I compare this with the model output, this is the model output, it's 0.011. Here the data is 0.01, and this is where I get an error signal. And I go from the error signal to this output, which is, this is going to be driving down the R0 in the model, right? So this is my the H of S filter that I described for the automatic adjustment of R0. Maybe I could do another video describing how I came up with this. I'm not 100% happy with it, I'll be honest, but you know, it's okay. It seems to be doing something. So we'll show you what it does. So this is the adjustment, and R0 is adjusted here by this value. And if I go back here, this is R0, and you see it's going from 4.15 to 4.14. And pretty much, you know, as we're going down, you see here R0 is dropping. Oh, now it's like almost leveling off and dropping. And this is all calculated by the transfer function H of S that I described. So the next graph I want to show you is this one. And this here in blue, there is the model output, and the yellow dots or orange dots are the actual data points, you know, non-smoothed. And as you can see right now, and this is a log scale, so this is a model output, and you see the model is sort of tracking the data points pretty good. And this is done automatically through, you know, reducing the R0 to this H of S. So now what I want to show you is what R0 over time looks like using this. And then remember, this was my estimator. So if I go on the right here, this is R0, and it started out around 4.1. And from the moment I'm getting some data, this is the data points. As you can see, the systems automatically adjust, and it's not smooth because the noisiness in the data. Right, and here's the bad news. The bad news is that we're sort of going down, but look, it's a little bit of a bumpy ride, right? So you see here, and where I'm disappointed at this stage is it looks like, you know, my estimate or the estimator is, I thought we were like closer to 1, but it looks like at this stage, you know, we're still in the danger zone up here, and it's growing. So hopefully, either there's something wrong with the data points, my modeling is not right, and maybe things are better than this, but I'm going to keep track on this, and thank you for watching.